So at this point, we've seen sequences and limits, and we've even calculated a few limits by hand. And the one thing that that's probably convinced you of is that it's not very much fun to compute limits by hand. And so the next thing we're going to do is build up a theory which lets us compute complicated limits by computing simple pieces and then sort of grouping them together. This is an idea that's probably pretty familiar to you. In calculus class, you had the product rule and the chain rule and so on, which let you calculate complicated derivatives by piecing together simpler ones, and we're going to do exactly the same thing here. So the first theorem that you want to write down is proposition 2.11, which is called the arithmetic of limits. And here's the idea. We assume that we have two convergent sequences, an and bn, and then some number c, and we get all of these nice theorems relating the limits of these different objects. So the first one's sort of obvious. The limit of a sequence of the same number is just that number. The second one tells you that you can pull constants outside of a limit. That is, the limit of constant times an is the same constant times the limit of the ans. The third theorem tells us that we can split up the sum. The fourth theorem tells us we can split up a product. And then the fifth one tells us that we can take inverses. Okay. At least when it makes sense to talk about inverses. Okay. So that's sort of nice, and even nicer is that you can put these sorts of statements together to prove other related things. So for example, let's say we want to compute limit as n goes to infinity of an cubed. Well, this is just lim n goes to infinity of an times lim n goes to infinity of an squared, which is lim n goes to infinity of an times, well, the same thing. That is, we're just going to keep on using the sort of part D rule, the one that lets us break apart products, and we get exactly the thing that we expect, which is that the limit of the cube is equal to the cube of the limit. All right. So you can sort of guess for yourself, okay, I can do cubic polynomials, probably I can do every polynomial, and indeed that's the case. So you can see how you can quickly build up functions. Now I did cheat a little bit when I was doing this calculation, and so if you saw it while I was going, then that's great, and otherwise, well, it's something that we do have to be a little bit aware of, in that the first line I wrote down this limit here is equal to this product of other limits, and I didn't quite check that the conditions of the theorem were met. In particular, right, in order to use this theorem, I need to know that both of the limits that are the constituent parts actually exist. Now this one I assumed existed. This one I didn't yet check. Now it turns out to be okay, because when I use the rule the next time, I can check, oh well, the limit of an squared, that's just the limit of an times the limit of an, and these ones I do know exist. So these ones exist, so that's fine, and because these ones exist, I can use the theorem to check, well, that one exists too, and so everything's okay, and indeed this calculation is correct, but it's not quite correct in the order that I was doing things, because I didn't quite check as I was going along that all of the conditions were in fact met. So this is a very powerful proposition, and it's fairly easy to use, but you do have to be at least a little bit careful that you're not doing anything invalid in the steps in the middle. You can sort of check backwards when you've finished a calculation that everything was okay, but you do have to check somewhat carefully that you didn't, for example, have something that was 0 in the middle, which is going to invalidate a bunch of your calculations. All right, with that out of the way, let's continue and talk about some of the later propositions. So the next one, proposition 2.12, sort of almost obvious, and here's the idea. If I have two sequences, an and bn, that are convergent, and furthermore, an is always sitting below bn, well, then the limits have the same relationship. So what's the proof? Well, I'm going to use more or less the same trick that I did before of breaking apart a sum by adding in a 0, or in this case, something that's less than 0, in a careful way. So, as with many of these proofs, I'm going to say fix some epsilon greater than 0. Then there exists some capital N depending on epsilon, so that for all n bigger than n, an minus a and bn minus b are less than epsilon over 2. Now I'm cheating a tiny bit here. That's not really quite the definition of the limit, right? In principle, I should have some capital N associated with this sequence, call that NA, and some capital N associated with this sequence, call that NB, and then this big N here is the maximum of those two. So I didn't do that little step of writing down a separate sequence for each one. You can check for yourself if this bothers you that in fact this is completely fine, and it's not a bad exercise to do that at least once. In any case, this is completely fine. It does in fact follow almost immediately from the definition of a limit, and so I'm going to keep on going from here with my calculation. So having fixed some big N, I now say, well, for n bigger than n, I'm going to do a calculation, and I start off by saying, well, since bn is bigger than a, 0 is less than bn minus an, and now I'm going to do my favorite thing, which is adding and subtracting something. So this is less than b minus a plus bn minus b minus a minus an. Okay. Great. Oops. Plus a minus an. All right, having done that, we can now take away absolute value. So this is less than b minus a plus epsilon over 2 plus epsilon over 2, which is less than or equal to b minus a plus epsilon. So putting all of that together, we find that a minus b is less than or equal to epsilon for all epsilon greater than 0, since epsilon was arbitrary. So we've shown that a minus b is less than or equal to epsilon for all epsilon, and in particular that means that a minus b must in fact be less than or equal to 0, which is exactly what we wanted to prove. Okay, so that's the argument, fairly similar to some of the arguments we've seen before, where we're effectively adding and subtracting in the objects that we wish to compare. All right. I think not a lot to say in terms of that one. It's not sort of completely obvious how you'd use that theorem to actually do calculations. It's more of a theoretical tool that we'll come back to later. The next theorem, though, is surprisingly useful for calculating things, even though it looks fairly similar. So this one gets a name, both in the lecture notes and also if you look online. It's often called the squeeze theorem. So here's the theorem. It has three very similar conditions. I have two sequences, an and bn, but this time they converge to the same thing, which I'll call L. And then finally, I have a third sequence, xn, which gets squeezed in between them. That is, an is less than or equal to xn, which is less than or equal to bn. And the theorem is, well, if an converges to L and bn converges to L, and xn is sitting in between them, then xn has to converge to L as well. So what's a proof of that? Well, we can sort of almost do a proof by pictures, right? So we have here, I've drawn the limit L, which is just a straight line. I have in blue my sequence bn up top, and I have in green my sequence an at the bottom. And we sort of know that, well, whatever xn is doing, it's sandwiched in between these things, so it's sort of wiggling along here and it sticks around there. And of course, those two get closer and closer together, and so what can the xn possibly do except converge to the same object? And that picture is actually sort of almost a proof. I just have to zoom in at the end here, where an and bn are both sitting within epsilon of their limit L. And I can check just by looking at the picture, well, if both of them are within epsilon, then surely this sort of rainbow line that I've drawn, it also has to be within epsilon, because it's sitting there, sandwiched between the two things, which are themselves sandwiched in this interval of width epsilon. So really all that we need to do to prove the theorem is turn this picture into mathematics. And we're going to do that the same way we proved the last theorem, by doing this sort of little triangle inequality trick. I'm doing the picture because it's sort of worth pointing out that actually if you look at the picture, that really is about 99% of the proof. And if the proof is giving you trouble, in some sense the trouble is almost certainly in the translation step. And the good thing is that the translation step is probably the easiest part to practice. So how do we do this? Well, as always, we start off with all of these proofs, fix some epsilon bigger than 0, then, since an converges to L and bn converges to L, there exists some n, oops, I forgot that part. There exists some n, depending on epsilon, so that for all n bigger than n of epsilon, an minus L and bn minus L are both smaller than epsilon in absolute value. Okay. So that's sort of the boilerplate, right? All of the theorems start this way, or all of the proofs start this way. And the next part is we just have to turn this little bit of the picture into mathematics. So what's going on there? Well, Since we have an minus L and absolute value is less than epsilon, we certainly have that minus epsilon is less than an minus L. An is less than xn, so this is less than xn minus L. Xn is less than Bn, so this is less than Bn minus L. And then in the other direction, using this inequality, Bn minus L is less than epsilon. Okay. So that's really just translating this thing here, right? We have this sort of three-part picture. We have this minus epsilon thing at the bottom. And then when we're walking up this picture, the next thing we hit is this green line, which is an minus L. And we keep on walking. The next thing we hit is this rainbow line, which is xn minus L. The next thing we hit is the blue line, which is bn minus L. And then the last thing we hit is this top part of the curve, which is epsilon. And that's exactly what's going on when we write down this inequality here. And if you just sort of look at the terms, this one, and this one, what we've shown is exactly that xn minus L is less than epsilon in absolute value, which is exactly what we need to get the conclusion that we want. Okay, so this is a fairly quick theorem to prove, and a very important one, and maybe one of the things that I wanted to emphasize again is that you can more or less prove it with this sort of picture, almost as good. So let's use both of the theorem, or two of the theorems that we've written down to actually calculate some limits. So the first time we're going to use the arithmetic theorem and calculate the limit as n goes to infinity of this sum of this ratio of polynomials, so n squared plus 2n plus 1 over n squared plus 7n plus 12. So how do we do that? Well, the first thing we use, we're going to divide through by n squared, so this thing here is equal to this thing here. And then, well, I'm going to be a little bit informal here, and it's not a terrible exercise for you to do to be completely formal in all of this. We've already shown that 1 over n converges to 0, and exactly the same proof is going to tell us that 2 over n converges to 0, 1 over n squared converges to 0, 7 over n converges to 0, and 12 over n squared converges to 0. So those first level arrows that I drew, those are all things that you can prove directly. So those are the simple limits that we know how to do. Now, using my arithmetic rule, I can look at this big thing in blue, and I can take the limit of that entire sum. So this first thing is converging to 1 because it's a constant. This thing is converging to 0. This thing is converging to 0. Limits of sums are the sums of limits, so this whole thing is converging to 1. And I can do the same thing at the bottom. That whole thing is converging to 1. And then finally, I know that this top part of the fraction converges to 1, and the bottom part of the fraction converges to 1, and we have some nice rules for dealing with entire fractions. And when we use those rules, we get that the entire thing converges to 1 itself. Why do I have all of these funny circles? Well, this is how you use the arithmetic of limits properties if you're doing it, in fact, carefully. So this is informal in that I'm drawing pictures rather than doing lots of arithmetic on the page, but it's not sloppy at all, and it's in fact less sloppy than the derivation I had at the very beginning. This is really the order in which you wish to prove things. That is, if you want to use the arithmetic rules, the first thing you do is these black arrows. You prove some simple limits. And the next thing you do is you're going to group up a bunch of those simple limits using these blue arrows. And you can use the arithmetic rules to sort of combine all of those limits into a big one, which is 1. And at the bottom, again, use the arithmetic rules to combine those limits into a single one, which is 1. And then finally, use a green arrow to sort of lump together those limits that you computed. And so that's how these structures are always going to work. You compute some elementary ones, you group some terms and compute those, you group some other terms and compute those, and you keep on grouping and grouping and grouping, and eventually you've computed the entire limit. All right. So that's sort of the basic structure of a proof using the arithmetic rules. Now we're going to do a basic structure of the proof using the sandwich theorem. So here's sort of a more generic theorem. I'm not going to try to prove something about a particular sequence. Instead, I have the following. Fix some sequence an that's bounded. Then, conclusion, the sequence an divided by n is convergent, and in fact it converges to 0. So here an may or may not be a convergent sequence. So for example, an is minus 1 to the n, right? That would satisfy the conditions of the theorem, but it's clearly not convergent itself. Okay, nonetheless, an over n, that is going to be convergent, and it's going to converge to 0. So how do we prove something like this? Well, this is one of the simpler applications of the sandwich theorem. So an is bounded, and so I'm just going to give names to some upper and lower bounds. So there's this little m, which is less than an, and capital M, which is bigger than an. Then what do we know? Well, then m over n is less than a over n, which is less than capital M over n. And these limits are ones we can calculate. This clearly goes to 0. This clearly goes to 0. So we have a sequence which is sandwiched between two things that go to 0, and so we conclude that this thing goes to 0 as well. So that's it. That's how you use the sandwich theorem, and there's probably not a whole lot to say about that. In the remainder of this section, we'll learn how to calculate even more limits. Thanks.